Every enterprise engineering team attempting to build an internal AI agent eventually hits the exact same scaling wall. They can easily get an LLM to answer basic questions, but the system collapses the moment it's asked to process the multi-hop dependencies inside a custom codebase or a 10K filing. To see why, look at the sheer volume of global information. By 2025, we will generate roughly 175 zettabytes of data. And as this chart shows, 80% of that volume is dark data, ancillary information that currently sits unanalyzed inside enterprise boundaries. This dark data isn't just raw text. It is highly structured intelligence stored in relational databases, nested spreadsheets, and forensic financial reports. It contains a strict internal logic that standard AI pipelines simply cannot see. The disconnect is architectural. Large language models operate as next token predictors. They are mathematically optimized for linear text, reading one word after the next in a straight line. Forcing a multi-dimensional database into a linear text predictor destroys the logic of the source material. This mismatch is what creates the enterprise scaling wall. We can identify the specific failure point at the moment a relational database or a 10K table enters a standard AI ingestion pipeline. This schematic shows the physical destruction of the data. On the left, the pipeline takes complex tabular relationships and flattens them into isolated paragraphs of bracketed text. Compare that to the right. A structural encoder preserves relationships, explicitly maintaining the logical context. When you flatten data like the example on the left, you get semantic slop. The AI retrieves a revenue snippet from 2021 and a cost of goods sold item from 2022, entirely disconnected from their original headers, and confidentially stitches them into a lie. The moment tabular alignment is destroyed, sorting context and numeric thresholds vanish. The AI no longer knows if a number represents a minimum, a maximum, or a specific accounting code. Enterprise AI hallucinations are rarely caused by an unintelligent model. They are almost exclusively the result of a data structure that was shattered during ingestion. When models fail on structured data, the first instinct for many engineering leaders is to initiate continuous fine-tuning. Fine-tuning changes the model's internal weights. This adjusts its tone, its behavior, and its familiarity with domain-specific jargon. However, it does not act as a reliable database for factual retrieval. The compute cost is massive. Enterprise data changes daily. Keeping a model updated through fine-tuning requires expensive, perpetual training loops just to keep the AI aware of yesterday's transactions. This creates a hallucination trap. A model trained on a product manual doesn't know the facts. It knows the statistical probability of word sequences that sound like that manual. It will confidently guess the details it can't remember. Fine-tuning is the equivalent of sending an AI to medical school to learn a better bedside manner. If your goal is a forensic audit of real-time facts, you don't need a model with a degree. You need an open book exam. Retrieval-Augmented Generation, or RAG, provides that open book exam. It connects a frozen model to dynamic data, allowing for real-time updates without retraining. The matrix shows the trade-off. Vector RAG is excellent for data freshness, but it fails on tables and graphs. Because it treats all data like a flat list of text, it loses the structural signal required for forensic accuracy. Standard RAG relies on cosine similarity. It calculates the mathematical distance between word embeddings to find relevant text chunks based on proximity. This makes vector RAG a map of roads. It can find the path from point A to point B, but it has no idea what happens inside the buildings. It navigates between chunks without understanding the logical rules governing them. This leads to the lost-in-the-middle syndrome. Critical context is ignored because the system retrieves isolated spans of text without their overarching structural links. While vector RAG solves the data freshness problem, its probabilistic nature makes it blind to the multi-hop reasoning required for forensic business questions. To fix this blindness, the industry turned to GraphRag. By mapping explicit node and edge relationships across documents, knowledge graphs attempt to restore the structural context that vectors miss. Looking at our matrix, GraphRag improves structural awareness, but the hallucination risk remains high. On many real-world tasks, GraphRag actually underperforms basic vector RAG. The vulnerability is shortcut learning. Instead of tracing a logical path through a complex query, the model gravitates toward highly connected hub nodes, generic terms that link to everything. In medical benchmarks like ShatterMed-QA, models using graphs often exploit these hubs to guess the answer, bypassing the actual micropathological pathways required for a correct diagnosis. This reliance on semantic approximation has measurable consequences. On the GraphRag bench dataset, GraphRag frequently underperforms vanilla RAG because its reasoning paths are built on superficial correlations rather than strict causal logic. The only way to eliminate semantic guessing is to move from probabilistic search to topology-driven architecture. Our final matrix row shows topology as the standout. It provides the only architecture capable of handling complex table structures with zero hallucination risk. It utilizes action topology format. This treats every document not as a string of text, but as a traversable logical structure with mathematically strict internal boundaries. The system uses high-speed community detection to derive concepts from data chaos. These aren't semantic guesses, they're absolute structural clusters that isolate specific logic. This architecture deterministically locks the AI into a specific logical room. If it is reasoning about ingress logic, it is physically impossible for the system to pull data from IAM roles. Treating data as a molecular topology enables deterministic grounding. In benchmarks across legal and medical logic, this architectural isolation has eliminated the specific hallucinations caused by cross-context contamination. To scale safely, you must match your business goals to the correct architecture. This decision framework provides the roadmap. If your primary mandate is teaching the AI a specific brand tone, style adaptation, or rigid output formatting, fine-tuning is the route. If the goal is querying basic, unstructured text like company handbooks or policy PDFs, vector RAG is appropriate. If the mandate requires accurate multi-hop forensic reasoning on financial spreadsheets and structured relational tables, topological architecture is mandatory. The performance ceiling of your AI agent is dictated entirely by how well your retrieval engine respects the structural complexity of your data. Moving from probabilistic vector search to topology requires an upfront architectural investment, a dedicated formatting phase to give your data its logical heart. But you balance that one-time cost against the endless, bleeding expenses of manual AI orchestration and the cleanup of semantic slop. AI models do not fail because they are inherently dumb. They fail because the underlying architecture is blind to the logical structure of the intelligence they are trying to process. For enterprise leaders, the mandate is clear. To scale AI safely with human-level exactness, you must build the buildings, not just map the roads.